So we've been discussing the modes in a step index optical fiber so far, right? So today let's discuss the modes in a graded index fiber, and specifically this popular square law profile. Right, so basically now the refractive index in the core is some function of position, right? So some cladding outside. So we can okay, so for the square law, for example, you can write the refractive index as you know like this, right? Right, so for example, this will be in the core. And in the cladding, it will usually be some constant refractive index. So we already looked at this kind of profile in a slab, right? In a planar slab waveguide, and we saw that we could solve for the modes exactly, right? Assuming that this profile sort of extends till infinity, right? So this profile, if I plot here, right, it looks something like this, and then it's constant, right? So this x, similarly with y, right? So this is n1 square, and it's n2 square here. Right, so again, if you want to solve for this profile exactly, then again we have to solve for the mode inside and outside and then use boundary conditions, right? So that becomes a bit complicated. What we can instead do is assume that this profile extends sort of forever, which is of course not physical, but the approximation again works well for well-confined modes whose effective index is close to this n1 and away from n2. Right? So first few lower order modes, right? So basically we just assume that this is the profile for all R. Okay, so yeah, so assumptions. One is that square law profile extends infinitely, like not just in the core, but even outside. And second assumption again we'll make is the weakly guiding approximation. Right, so this difference is small. Again, for the same reasons, like for practical fibers, this is true, and the modes then we can use and solve using the scalar wave equations, as opposed to the exact vector modes.
So what?
Yeah.
N2 square equals to N1 square then?
N2
So
square
the
equals
second line, reflection of light is coming, that's why it's not clear.
Oh, so right. So this is equal to, I mean, you can put R equal to A here, right? Right, so we'll make these two approximations, then basically we can use the scalar wave equation under the weakly guiding approximation. Right, where psi is the mode profile. So, for example, again we can take sort of linearly polarized modes. So, for example, either Ex, right, or Ey. These would be degenerate modes, just like we did for the LP modes in a step index fiber. Right. So the only difference here is now, so this is a function of position. Right. So again, so for the slab, this was just a one-dimensional. This was n square of x, and then we went ahead and solved this differential equation. Right. Now here, of course, there are two dimensions. Right. So, and you can sort of see that the structure is cylindrical symmetry. So you would think that okay, we have to go ahead and solve this in cylindrical coordinates. But turns out that for this kind of refractive index profile, right, we can actually solve this in Cartesian coordinates also. Okay, so we'll see how we do that. So we can exactly solve this in Cartesian coordinates. Right, so x. So basically, we rewrite this equation in Cartesian coordinates then. And actually, one advantage of solving it in the Cartesian coordinates is actually we can generalize this to different types of fibers, right? So, for example, let's say you have an elliptical core. Okay, instead of circular core, let's say you have an elliptical core. So along the x-axis, the core size is A, while along the y-axis, the core size is B. Okay, so it has an elliptical core. Okay, so let's say you have an elliptical core and then a square law profile within this core. So, for example, I could write so into here outside. So okay, so for example, I could have a profile like this. So it starts from N1 in the middle here and then goes to N2 at the boundary of the core, but the core is elliptical, right? So basically the refractive index profile looks like that. Okay, so I can, if in the Cartesian coordinates, we can solve for a refractive index profile like this in general. Okay, and you might think that this looks strange. Why would we want like an elliptical core fiber? But for some applications, right? So, for example, there are these polarization maintaining fibers. Okay, where basically we want the polarization of the light we send in to be well maintained. Okay, and these fibers have elliptical cores. Okay, so you can see that. So basically, once you have an elliptical core, you break the symmetry between x and y, right? So you can imagine, for example, an x polarized mode will have a different propagation constant than the y polarized mode, right? And so that would prevent mixing between the x and y, right? So now they are orthogonal modes with different propagation constants, right? Whereas here in a circular core, the x and y, as we know, are degenerate modes, right? Which means any small deformations along the fiber can sort of mix the x and y components, right? And what that leads to is like distortion in the polarization and what is known as polarization mode dispersion. Okay, which probably we'll study later in the course. Okay, so to avoid that, one can use these polarization maintaining fibers which have elliptical pores. Okay. Anyway, so the point is that we can solve for even such kind of fiber with this gradient index if you use Cartesian coordinates. Okay, and then for A equal to B will be the special case for our usual circular profile. Okay, so now you can see, for example, so this is now a function of R and phi, right? Not just R. So if A is not equal to B, then this is now a function of both the radial and azimuthal coordinate. Right? So actually for such a refractive index profile, it becomes difficult to solve in the cylindrical coordinates because now you have a function of both R and phi. Okay. So if it was just a function of R, as we've seen, then you can still solve it in cylindrical coordinates. We'll see that later. But if you have a function of both R and phi, then actually it becomes difficult to solve in cylindrical coordinates. But we'll see that in the Cartesian coordinates we can solve it. Okay, so again, we assume the mode profile to be the usual. So we have a mode profile in the cross section and then a propagation phase. Right? And yeah, so we plug this into the wave equation here. So in Cartesian coordinates, we get right. So again, for the z component, the double derivative will give me minus beta square, and then the time derivative double derivative will give me omega square. Right. So the k naught. Okay. So now again, the function here, right? It's a function of x and y, but it's a function of x plus function of y. Okay. So, for example, there is no xy term here, right? And so now, if you have something like this, what you can do is use separation of variables, right? So we did that also, for example, when we solved for the LP mode with step index fiber in cylindrical coordinates. We used separation of variables because we ended up with a sort of function here which was sort of like just a function of r plus just a function of phi. Okay, so similarly here we have just a function of x plus just a function of y. There is no cross terms. If you write this in the r phi coordinates, you will have cross terms. Okay, so that's why I said it's difficult. That would be difficult to solve in the cylindrical coordinates. But in the Cartesian coordinates, this is basically a function of x plus function of y. So you can see that we could separate this into an equation of just x plus an equation of just y. Okay, so you can use separation of variables. So which means basically we write this as a product, a function of just x and a function of just y. So if we plug this for psi into the equation here, and then divide the whole thing by x times y. Okay, so we end up with okay. So yeah, straightforward. So basically we separated out the terms. So this is just, again you can see a function of just x. This thing is just a function of y, and this thing is a constant. Right? And they all add up to give 0. So the only way that can happen is both these are also constant. So this is also a constant and this is also a constant. Okay, so we put that, so this we call minus kx, capital K to ky, right? And this constant would then minus, so be kx plus ky. Okay, so again, same thing is true now for guided modes. Basically, we want beta to be less than k0 and 1. Okay, only then they correspond to guided mode. Right, so that means this quantity is positive. Right, so that's why we take these two to be negative, which cancels out this positive part. Okay, and now we do a change of variables. Right, so now this is starting to look like what we had for the slab. So in the slab we just had one dimension, so we had one equation. So we just had sort of like this part. Now we have sort of another identical copy of that equation in the other dimension. Okay, so it's like almost like we have two different slab equations together. Okay, so again we can do the same, solve the same way. First do like a change of variables to normalize things. Okay, so because so you can see with x here we have this term. Okay, so you can write this as some v parameter in the x direction. Okay, so the v parameter in the x direction is that, right? So the size is the x direction. Similarly, v parameter in the y direction will depend on the size in the y direction. Okay, so if we do this normalize change of variables and then write this equation again, so you get simple forms like this now. Right, so this is for x and similarly for y. Okay, so we end up with the same equation that we had for a gradient index slab. Right, so this is the same equation. Instead, now we have two equations. for the 2 dimensions. Right, so what are these capital gamma? Right, and so now we have this equation that, if you remember for the slab, we solved it. Right, so we assumed that this x now is like a polynomial function multiplied by like a Gaussian function, right? And then we substituted this and then did some algebra and then found out that this capital lambda has to be an integer, right? For the polynomial to be a finite series, right? And then we found the relation between the coefficients. So same thing. We have the exact same equation, so exact same solution in each dimension.
So what lambda x and lambda y you have written at last?
So yeah, lambda x is k1 by gamma x square and lambda y is k2 by gamma. So sorry, kx. So kx, ky, kx by gamma x square and ky by gamma y square. Okay, so we won't go through that same analysis once again, right? You can refer back to the notes of the slab. Basically, so now for solutions which decay to 0 at x and y equal to plus minus infinity, basically this capital lambda x and y have to be integers like that, right? So m is 0, 1, 2, some integer. Right? And the solutions for x and y are the Hermite Gaussian functions. Same thing that we got for the slab, right? So for m here, for a particular value of m, this will be the Hermite function of the mth order times the Gaussian function. Right, and some normalization constant. Right? So this normalization constant is okay, just so for this to come out to 1. Very similarly, the normal response is the same, just replace x by y and m by n. Okay, so these are the Hermite polynomials again, right? Defined in the same way that we defined for the slab. And then, right, so now, so if this capital lambda we know is some integer, from there we can get capital Kx also some integer times this gamma x square, right? So gamma x just depends on the fiber parameters. So we can get capital Kx and capital Ky now, once lambda x and lambda y decided, right? And from that now we can get beta, comma n mod, right? Mn. So again, we have two indices here, right? Because it's a 2D structure again. So we'll get the same expression that we had for the slab, except we have two of those, right, for each dimension. Okay, so for the slab we just had this, so now we have another one. And we have two indices. Sorry. Right, so this is basically your capital Kx and this is capital Ky. Or this is capital Kx because K0 N1. So again, right, so these, so if delta is small, which we started with that assumption, right, so this delta is small, so this quantity here is small. So for example, right, so if you take delta of 0.01, N1 to be 1.45, and port size, let's say 25 microns, then this value here, root 2 delta K0 N1A, is about 10 to the minus 3. Right, so you can see for small values of M and N, this value will be very small compared to 1. Right, so again we can use the Taylor expansion here. Okay, so we can get this expression for the propagation constant. So there is only one term which depends on frequency. So K0 we write as omega over c. And then this thing which goes with M and N, but these are constants, right? So again, if we take the group velocity for the Mn mode, that's the derivative of the beta with respect to omega, so that's just a constant M1 by c of E over N1 Vg. So it does not depend on M or N, right? So this implies that all the modes travel with the same speed, and so there is no intermodal dispersion, at least to first order, right? Because we use the Taylor expansion here of the first order. Okay, so again, just showing that gradient index fibers have lower dispersion than step index. Right, so basically now, yeah, we solved for the modes, right? So there is this Hermite Gaussian functions. We have two of them, M and N, and the total mode is the product, right? X times Y is the mode profile. So these are known as TEM and then indices MN modes. Right, so again, starting from the weakly guiding approximation, we've already assumed sort of that the modes are mainly transverse electromagnetic, right? We've taken the electric field transverse, and then from the curl equation we get the magnetic field also transverse, and the longitudinal components are negligible. Right? So there's another reason why they're called TEM modes is basically if in a laser cavity, if you have a laser and free space, like you have 2 mirrors and you form a cavity, laser cavity, sort of the spatial modes that you get in the laser are also the same modes. Okay. So in a free space laser cavity, you get the same modes, and from there, sort of, they've been named as TEM domain. So let's consider the usual case of most fibers, right, where I have A equal to B, so a circular core. And let's look at the mode profiles, how they look like. Okay. So if we take now the lowest order mode will be M and N both 0. Right, so then you can see, so for the 0th order Hermite function is just a constant. So they are both Gaussian functions. So when we multiply the two, so here we get e to the minus x square, here we get e to the minus y square. When we multiply the two, we get x square plus y square, which becomes r square. Okay. So the mode profile now just looks like a Gaussian in radial coordinate. Okay, I can also write it like this. So now we have this B number. So now for A equal to B, Bx and By both are the same. So we denote that by B. Okay, so it's a Gaussian in the radial coordinate, right? And you can see that the size, the spot size, depends on the B number. Okay, so for example, if I write this as some e to the minus r square by w square, where w is now the spot size, right? So then the spot size you can see from here. When the spot size is the core radius times something which is proportional to, inversely proportional to the square root of b. So as the b number increases, the spot size goes down. So for example, I mean, if you increase the core size, then A is also increasing, right? So then you can see that actually the spot size will increase because the core size is increasing. But if you increase V number, for example, by reducing the wavelength, so A is constant, in that case you can see the spot size will go down. Right, so the mode is more confined for smaller pixels. You expect anyway. So how do the modes look like? So now the profile is a Gaussian in the radial coordinate, and again, it could be either x polarized or y polarized, right? So we started with just a scalar wave equation. So the solution was we could have for either ex or ey. So right, so they're linearly polarized. And then the mode profile looks like a Gaussian in radial coordinates. I mean, you can take any direction, any radial coordinate, it will look like a Gaussian. Right, so this will be the y polarized mode. You also have a degenerate x polarized mode. So this looks pretty much like the LP01 mode, like the fundamental mode in the step index factor. Right? So the TEM00 mode looks basically like the LP01 mode. Of course, the function is slightly different. Right? Here you have an exact Gaussian for the gradient index, whereas recall for the step index you have the Bessel function. Okay, now let's look at some higher order modes. So the next higher order would be either you make m equal to 1 or n equal to 1, right? And again they'll be degenerate. So for example, TEM01. So now you will have 0th order Hermite function in the x coordinate, but the first order Hermite function in the y coordinate. So the first order Hermite function is a linear function, right? So there is no x here because 0th order is just a constant, but you'll have a y here coming from the first order Hermite function, and then the Gaussians in the x and y again add up when you multiply. So again you get r squared here. Right, so now it's y times this Gaussian function. So you can see, so basically at y equal to 0, you'll have the mode will go to 0. Right, so again, if this is the y coordinate and this is the x coordinate, again we have two degenerate modes. So at y equal to 0, the mode goes to 0, so you have two lobes like this. So again, you could have bipolarized or x polarized. Right, so the mode profile in the x direction looks like a Gaussian again, but in the y direction, it's this Hermite function of the first order times Gaussian. So it's like that. Right, so this is coming from like x0 times Gaussian, and this is like h1 times Gaussian. Right, and TEM10, you just swap x and y. Right, so you can see from here the propagation constant. So if A is equal to B, it just depends on m plus n. Right, so again 0, 1 and 1, 0 will be degenerate modes. And yeah, so now you'll have a null in the x equal to 0 direction, right? So two lobes like this, and again now you can have y polarized or x polarized. Right, so now you can see these look like sort of like the LP11 modes, right, which had fourfold degeneracy in the LP11 modes. These four modes look like the four degenerate modes for LP11. Right. Okay, so you can see the degeneracy here is much higher. I mean, modes with the same m plus n have the same value of beta, so they're degenerate. Okay? So for example, if I go to the next now, so if I go to 2, so 0, 2, 2, 0 and 1, 1. All these three modes will be degenerate. Okay, so maybe we can just see so how 1, 1 looks like. Right, so basically as you increase the order of either, so if you increase the order of m, then you get another null in the x direction, right? You get another 0 in the x direction. If you increase n, then you get another 0 in the y direction. So 1, 1 means now we'll have x times y. Right? So I'm ignoring the constants here. So we'll get a function which is x times y times Gaussian in the radial coordinate. So now you can see this will look like. So now I'll have a 0 in both along the x equal to 0 and y equal to 0 directions. So that means I'll have 4 rows. Right, again, so now I could have y polarized or x polarized, and the phase flips from each lobe to the next. Right, so again, if you look at the cross section, so the mode profile, so now in both the x and y directions, you have the first order Hermite Gaussian function. Right, so in both the x and y, you have first order Hermite function. Okay. So yeah, so that's basically this is a discussion on the TEM modes, which we solved using Cartesian coordinates. Okay. The next thing we'll do is we can also solve it in the cylindrical coordinates, right? Because the structure has cylindrical symmetry. So, for example, in the step index, we solved it in cylindrical coordinates. So then, of course, for A equal to B, right? For A not equal to B, it does not have cylindrical symmetry. So for that, you have to use these Cartesian coordinates. But if A is equal to B, then it has cylindrical symmetry, and we can also solve the wave equation in cylindrical coordinates. Okay, just like we did for the LP modes in the step index. So we can do the same thing here, and we'll get LP modes for the graded index. Okay, when we solve in the cylindrical coordinates. So we'll do that next time. So we'll solve for the LP modes in the graded index, and we'll see. So of course, you can both are equivalent, right? You can solve in Cartesian or cylindrical. So the modes that you get, so you could have these modes or those modes, right? So basically, you should be able to write, for example, the LP modes as a superposition of degenerate TEM modes, or equivalently TEM modes as some superposition of degenerate LP modes, because both are equivalent. So we'll see how it comes about. Yeah, so we'll do that next time. Any questions? Right, so again, one thing to note here in the graded index, like for the square law, is that we can get an exact, we can get an analytical, right? Recall in the step index case, we did not, we could not get any expression for beta, right? There were solutions to this transcendental equation, and yeah, so basically for each For example, each b value we had to solve numerically or graphically, and then find the value of beta and do that for each point, right? But here you have an analytical expression already, right? So for example, you can straight away plot the BB curve using this equation.